Hello, everyone. I'm Justin Maresco, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on seismic analysis and design of non-structural components and systems. This webinar is made possible with funding from the ATC Endowment Fund. The purpose of the ATC Endowment Fund is to support efforts of critical importance to structural engineering design practice, research, and education. More information about the ATC Endowment Fund can be found on our website. If you haven't already, you can download the handouts using the link in the chat. We know that many of you are interested in receiving professional development hours for your participation today. Registrants who would like a PDH certificate must attend the full duration of today's webinar and pay $25, which helps ATC cover some of the costs of hosting the webinar. A link for purchasing a PDH certificate will be sent via email by ATC to all registrants by the end of the week. If at any time during the webinar you have questions, please type them in the Q&A window in the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar. Please submit your questions as you have them rather than waiting until the end to submit them. We'll try to answer all the submitted questions. If there are any that we aren't able to answer live, we'll provide written responses to them after the webinar. So now that we've gotten through all of the housekeeping items, let me tell you about your presentation team today. Marianne Phipps is the founder and president of E-Structure in Oakland, California. She has nearly 40 years of experience evaluating, designing, and renovating buildings for earthquakes. She currently serves on seismic review boards for the University of California System and California State University System, and chairs the Seismic Review Committee at the University of California at San Francisco. Marianne was recently bestowed a Lifetime Achievement Award by the Structural Engineers Association of Northern California. Brett Lazundia is a structural engineer and principal at Rutherford & Jacquin in San Francisco. He has more than 30 years of experience in structural design of new buildings, seismic evaluation and rehabilitation of existing buildings, peer review and plan checking, and applied research and guideline development. He is a past president of the Applied Technology Council and the Structural Engineers Association of Northern California. I'd now like to turn the webinar over to Marianne. Marianne, please go ahead.
All right. Yeah, there we go. I'm delighted to introduce the subject today, and I'm going to be giving a big picture perspective. Brett's going to be taking care of all the details. And what I want to do is provide everyone with a comprehensive background and context for the code changes that Brett's going to talk about. This is going to be fairly fast-paced, so I'm going to jump right in. The goals, the learning objectives for today are to just basically understand and recognize the importance of non-structural components and understand the consequences to their damage in an earthquake. I want to talk a little bit about the uncertainty in this subject matter to give you a better feel for the level of precision that we need to be thinking about. And then we're going to look at the ATC 120 project, the NIST research effort that was really the underpinnings and the foundation for the code changes we'll be talking about. So to begin, the universe of non-structural components is vast. It includes everything from architectural components like cladding and ceilings and partitions to mechanical, electrical, plumbing components, equipment, and distribution systems. And then the fixtures, furnishings, and contents that go into a building to give it its function. So not only is the universe vast, but these items range in size dramatically, right? We have everything from a desktop computer to a data center, from a residential hot water heater to a bulk oxygen storage tank in a hospital, and from a chimney in a house to a precast panel in a high-rise. Now, not surprisingly then, if we look at the value of a building, this is the cost of systems in a building, sort of an average building in San Francisco built in the past few years. And what you can see is that most of the cost of the systems in the building are not structural. The structures, give or take 20% of the cost of the building. The contents, non-structural components are the other 80%. So non-structural components make up most of the cost of the building. So consequently, this is something we really do want to focus on when we're talking about earthquake damage. Not surprisingly then, because of the value they represent in the building, is the fact that in most earthquakes, most damage is going to be non-structural. Now, this pie chart of damage is just one building in one earthquake scenario. But the reality is that in most earthquakes, for most engineered buildings, most of the damage is going to be non-structural. And past earthquakes have certainly borne that out. Not only is it mostly going to be non-structural, even in small earthquakes, non-structural components can be damaged. So all of these images are from really small and short earthquakes. So hopefully that grabs your attention, and hopefully everybody recognizes that non-structural damage in earthquakes is going to affect all of us. It's going to affect us where we live, where we work, where we shop, where our kids go to school, and our national treasures. It's a big deal. So now let's shift and look at the consequences of non-structural damage. We usually divide it into three categories: risk to life safety, property loss, and business interruption. So let's look at each of those. Risk to life safety is pretty obvious, right? If something can fall over on you and seriously injure or kill you, that's a risk to life safety. The soffit that's fallen on the exterior of the school building clearly could have seriously injured the students, but it didn't happen during school hours. The image on the right, however, a precast panel that fell off of a building in the Whittier earthquake did kill a college student who was underneath it at the time. The other way that non-structural components pose a risk to life safety is if our life safety systems can't function. So here's some sprinkler damage. So if the sprinkler system isn't available to fight fires after an earthquake, that can pose a life safety risk. Similarly, if you can't get out of the building, if egress is blocked, that poses a risk to life safety. So let's talk next about property loss. If it costs money to fix it, that represents property loss. So it's a pretty easy concept to understand. What's equally important, and it may be even more important, is recognizing the consequential damage that can impact the losses. For example, when a water pipe breaks, the cost of repairing the pipe could be almost nothing compared to the cost of repairing all the damage from the water. And it's particularly true for pipes under pressure. And if they aren't turned off quickly, the cost and losses can escalate very, very quickly. And then business interruption. Many businesses will lose money if they can't get back into their buildings. And if you're a manufacturing facility, oftentimes those costs are measured in millions of dollars an hour. So business interruption can be a costly consequence of non-structural damage. So I want to shift gears and give a little bit of context to this field and the design procedures that we're trying to develop. So let's say we are interested in designing the supports and bracing for a suspended operating room light in a hospital. And what I want to just have everyone recognize is that the design is at the non-structural component is at the end of a very long chain of events that starts with the earthquake. So for example, we have an earthquake. We don't know exactly how far it is from our building. We don't know how deep the earthquake is going to be. We don't know what the fault characteristics are necessarily. And then we have these waves traveling through the ground. We don't really know what the ground is. We don't know how the attenuation relationship is really going to go. And then we get to the building. So now the building is being shaken by this earthquake, and it has its own dynamic response based on all its design parameters. And then finally, we get to the floor that is shaking with some deformations and some accelerations, and we get to the non-structural component. That component can be connected to the floor in many different ways. And so each of these has its own unique dynamic response to the shaking that it experiences. And then you've got it connected with all kinds of widgets and stuff. So the point is that there's a lot of uncertainty in that process. And to think that we need that the precision is valuable here is kind of a misnomer. Don't worry about too many decimal points. I think what's important is to get the science about right, to make sure that we're addressing all the elements that are important to us, and that we don't get too caught up in the precision of the design tools that we develop. So about 10 years ago, the NIST, National Institute of Science and Technology, got together a team of experts to think about what research they should be doing over the course of the following 10 years. And that group got together and wrote a report. And in that report, they identified non-structural issues as a top priority, calling for problem-focused studies in critical areas related to the seismic design of non-structural components. And that is how the ATC 120 project was initiated. And this NIST went to ATC. ATC started a project with the goal of improving the technical aspects of non-structural design to get the most bang for the buck, so to focus on the things that are most important. So this ATC 120 project is really the foundation on which the code changes we're going to talk about are built. The ATC 120 project ran like all good ATC projects. It was there were many experts involved from all walks of this field. We got together over a period of many years, and Brett and I were both leaders in this effort. The first thing we did in the first year or so was a knowledge study where we brought together everything that was kind of known so that we didn't duplicate what was known and we could build from that. This is a great document that's available for free and provides a really nice background for anybody who wants it. The subsequent years we spent trying to figure out all of the components to the problem. In other words, what are all the things that we need to study together to come up with how we should be designing, the answer to how we should be designing non-structural components. And you can't just look at one thread. We had to weave them all together. So we wanted to look at and evaluate the existing code requirements. We wanted to study parameters that affect non-structural component response. We wanted to use strong motion records that are available, so we have some quantitative information, and supplement that with analytical models of buildings. We need to investigate anchors to concrete because most non-structural components are anchored to concrete. We wanted to see if we could develop a design philosophy for non-structural components. And we wanted to look at the performance objectives that we should be using. So these are the kinds of things that we did as part of the ATC 120 project. And the effort resulted in a report that had 7 chapters. And I'm going to just highlight some of the aspects of these chapters to give you a sense of what was done and what's available. First, we're going to talk about performance objectives, because if we don't know what we're trying to achieve, we can't really do a very good job at developing code language, right? So it all starts with, what are we trying to achieve? So if we think about the objectives that are in the code, they are really twofold. One is that structures should have a low likelihood of collapse in the MCE. And 2, life-threatening damage, primarily from failure of non-structural components, should be unlikely in a design earthquake. And this is for a risk category 2 building, a regular building. And so we really were building from this code-based design objectives as we were developing code recommendations ultimately. So what we did first is think about the performance levels are appropriate to think about for non-structural components. And like we talked about before, we categorize them in terms of safety and property loss and loss of function. And so, for example, in safety, you see things like we want to maintain egress, we want to prevent fire, we want to prevent things from falling on your head. But of course, the performance objective is the performance level, this descriptor, coupled with earthquake shaking. And so what we have here is a matrix that shows our non-structural components divided into 2 categories: those that we don't need to have functional after an earthquake. That's the ICP of 1, importance factor of 1 components. And then those that we need to be functioning after an earthquake, I of 1.5. And we just kind of filled in the blanks here to see what we're trying to do and what things we need to pay attention to get the code provisions ultimately right. And mostly what I want to point out here is not just what's in the code and what the code is based on, but what it is not. And the code, again, is not, for most components, is not worrying about function, is not worrying about property loss. Those are things that if you really want to worry about them, and being up and operational after an earthquake is critical, you need to do something more. So anyway, there's a whole chapter on performance objectives. Then we looked at the current code and we studied, how it was doing and whether or not there needed to be any improvements to it. And the way we did that is we identified these sample problems, if you will, these design examples, and we had 5 different firms work through design problems to see if they could sort of come up with comparable answers and to see where the glitches were, to see where they had problems using the code, implemented the code, and understanding it. And from that, we got their comments, and then we went section by section in the code to create a roadmap for improvements that we wanted to see in the future code edition. The next chapter, understanding the response of non-structural components to earthquakes, is really the biggest chapter. It's the meat of it all. It's what Brett's going to be talking about, because what we were trying to do is understand the science behind the response of non-structural components. And I'll defer to him on that subject. Next, as I mentioned before, we wanted to see if we could develop a design philosophy for non-structural components. And we looked at whether we could design non-structural components like we do structures with a ductile fuse in them. And what we found is that while that is possible, it's not that easy. For example, here there's a component anchored with angles. And so you can imagine that the weak wave bending in the angle would be the fuse protecting the anchors. Totally makes sense. But when you go in the opposite direction, 90 degrees shaking, it's just not so easy because the response changes. So there's language, there's a whole chapter about this, and I'd say it's of interest, but not practical implementation yet. And then we have a chapter on the holistic approach to protecting non-structural components. And I kind of want to underscore the importance of this, because we spend a lot of time worrying about forces and deformations, but it is way more than the F sub P equation. If we really want to protect non-structural components, we have to think about a whole lot of other things. For example, we need to make sure that every component that goes in the building that we care about, somebody is assigned the responsibility of designing the protection for that thing. We have to make sure on the other end that there's somebody there to inspect it and ensure that it was actually put in properly. And if we go beyond the engineering, we can think even more holistically, a little more outside the box. What does it take to keep a building reliably operational after an earthquake? Well, maybe if there's something that you really need to be functioning, maybe you need to have another one for the just in case situation. Or maybe you need more shutoff valves so you can turn off the water if the pipe breaks. Maybe you have a contractor on board who's immediately available to repair things after an earthquake. Or you do things off-site in a location that's not going to be affected by the earthquake. Or you make sure that staff is available to help right after an earthquake and knows what they're doing. So the idea here is there to just recognize that in this, the field of protecting non-structural components to earthquakes has a very important engineering component. It also has other considerations that are equally important. There's also a chapter on recommendations that I'm not going to go into right now, but there's much more that can be done to really support the continued development and enhancement of this field. So in closing, I just want to say I hope that you get how vast the universe of non-structural components is, the consequences of non-structural damage and how important they can be and the losses that can accrue as a result, and that there are tools that we've developed based on the ATC 120 project that will go a long way to advance this field. So I'm going to hand it over to Brett. And if you have any questions from this portion, I'm going to please write them down into the Q&A now so that we can address them at the end. Thanks so much.
Great. Thank you very much, Marianne. Justin, is my voice coming through on the screen okay?
It is, Brett. Thank you.
Great. Okay. Well, thank you very much to Marianne for an excellent introduction, giving us the big picture on why non-structural design matters, and that it's not just about forces. It's a much more importantly a holistic view that involves many people and many issues to get it right. However, I have been assigned the task of talking about those details today. And so I'm going to give you a taste of those and what's coming in your future, since this will affect essentially every building that we design in America when this code comes in vogue. So I wanted to let you know what I'm hoping you will take away from this and and remember at the end of the presentation. I want you to have a feel for what are the things that matter in changing or influencing in a significant way how non-structural components respond to earthquakes. Some things are important, some things don't matter so much. Want to give you a feel for what are the key changes in ASCE 722 and the sort of documents that led up to that, which includes quite significantly the design force equation that we all use is definitely different. How we design the support structures and platforms that non-structural equipment and components sit on is changing significantly, as well as how we do design of distribution systems. And there are some resources that are out there that are available to you that we think are valuable. There's a design guide, a series of examples that includes non-structural component chapter where I'm drawing much of today's slides from. So in terms of how we're going to go about this, I'm going to talk about the new design equation, give you a summary of kind of the research that went into that and how we ended up with the equation that we did. There were some other changes that are in chapter 13, the non-structural chapter, and chapter 15, the non-building structures chapter, that are coming in ASCE 722. And then I'll go into detail about one example, precast concrete panels on the cladding of a building. And then I'll give you just sort of a taste of what's included in 4 other examples. All of these can be found in that design example guide. And I'll give you links to that at the end of the presentation. So let's talk about the new design equation and how we got there. So like a lot of things in the building code, it doesn't come fast. And that's because there's a lot of people involved, there's a lot of research involved, there's a lot of vetting, there's a lot of commenting, a lot of thinking, a lot of consensus building. So people have been doing, good research on non-structural design for decades. And that kind of led up to this seminal moment that Marianne was talking about, where NIST commissioned ATC, which initiated the ATC 120 project, particularly its second phase, where we were focused on the design equations. So one task was to carefully synthesize relevant work that had been done, to do our own research, which was pretty significant. We did quite a lot, and there were a lot of people, professors, grad students, practicing engineers who were involved in that. And then eventually we developed a recommended equation. So that's nice. It's in a document. It has no force of law or in any kind of standard. So then if you want to actually get something into a code, here's what happens. In the United States, there's the Building Seismic Safety Council, which has a provisions update committee, the PUC, that works on a 5-6 year cycle. And during 2018 to 2020, one of its issue teams took on the work that came from ATC 120 and then developed code change proposals, reviewed them, balloted them, and eventually that pleasantly passed and was published in what is called the NEHRP Provisions. So the NEHRP Provisions is a very important document. It's basically what feeds into ASCE 7 on the earthquake side. And then in turn, ASCE 7, which actually is an ANSI standards process, they have their own code committee. It has a seismic portion. It even has a non-structural issue team made up of many of the same people that were in the PUC effort. And through the long process, it was eventually approved. And that was published at the beginning of December of, should say 2021 there, sorry. So it's out there, it's available, and it has to get adopted as the reference document into actual code. So the IBC, will become part of the 2024 version in California. That in turn will become part of the 2025 CBC. I'm in California, so you'll see some California references throughout this. So one of the things that we did at the beginning of this project is we said, you know, we need to talk about terminology. And why is that? Well, it's because everybody in all these research things have been using sort of different terms for similar things. And if we don't have a common language, we're going to not be able to communicate clearly, and we're not going to be able to synthesize this work. So this little snapshot on the right, you know, where the black earthquake squiggly line coming into the ground, that's the peak ground acceleration. That then shakes the building, and we go up to, say, the 3rd floor. And at that 3rd floor, we have a peak floor acceleration that is typically higher than that peak ground acceleration. And then there's something sitting on top of that floor or hanging from the bottom of that floor that's a component. And it wiggles around, and it has its own dynamic characteristics, and its characteristics in concert with the building characteristics and with the earthquake characteristics lead to a peak component acceleration, PCA. So we said, okay, let's gather the past information, let's put our heads together, and let's think about things that we want to investigate. And see how much of an influence they do or don't have on the response, that PCA response of the component. So you can see a pretty healthy list here. The ones that are in bold black are the ones that we found that were important and we were going to investigate in detail. We were a little surprised to discover building damping doesn't make too much of a difference. Building configuration, plan and vertical irregularities definitely does. If you have a component sitting at the outside edge of a building that's twisting more around than it is at the center of rigidity, then certainly it matters. And if you have a component that's on a wood big box, kind of roof versus a rigid diaphragm, definitely there's different response. We concluded that was just too complicated to include into the building code. It's not that it couldn't be done, we always have to strive of being sort of practical and not excessive. So we decided after a lot of soul searching that we were going to take those out. So I'm going to go through the rest of these things kind of one by one and show you what they mean and how and what we found from both recorded efforts as well as individual project specific research. So here is some discussion about, does the seismic force resisting system matter? Okay, currently in ASCE 716, this is not part of non-structural design. You can, it doesn't matter if you're in a shear wall building or a steel moment frame building, you get the same design force. Okay, does that make sense? So let's say that we add a component that is wiggling around and has a half-second period. And these are on the y-axis, this is the peak component acceleration divided by the peak ground acceleration. So we've normalized the ground input and we said, okay, what's the increase in response up at that component, up on the, somewhere in the building versus the ground. And you can see that for the shear wall building, which has a stiffer lateral system, that it is more in resonance with the half-second period of the component, and you can get a kind of a mean increase in response of a factor of 6. That's a big increase, right? Now put it in the steel moment frame, which doesn't have this as much of resonance, and it's a factor of like 3. So this is an important finding. It's not earth-shattering in terms of structural dynamics, but it's pretty compelling. What about the building modal periods? So let's focus just on the fundamental mode for this presentation. And what these pictures are showing at the top are a couple of different things. So one thing is, how does the peak floor acceleration vary with respect to the ground acceleration? So this is on the x-axis now, as we go up the building. So the roof, Z over H, Z is the height. So when you're at H over H, that you're at 1 at the top. and then the ground is 0. The blue line is the short period building. The red line is a longer period, you know, a high-rise building with a 4-second period. So what you can see is that the blue line is always to the right of the red line. That means that the amplification of a short period building is higher than a long period building. Not necessarily an obvious finding. And there's a more subtle one too, which is you can see how the shape on the right, the far right screen, they're more linear. The blue and the green, they're more linear. As we go to the left and we get, you know, a building that behaves, you know, differently. You know, we have shear response versus cantilever, you know, moment frame versus cantilever response essentially. And the ones on the left, the cantilever response, they have more of a whipping action. You know, things go up and then they start to increase more at the top. So this actually came out of some research that Professor Miranda did with one of his graduate students years ago, and has been sort of revalidated with more recent efforts. One of the things we found that we liked a lot is to capture this idea of resonance. We thought of normalizing the period axis with the component versus the building. So let me talk about what that means. On the left, this is sort of kind of a classic kind of response spectrum kind of plot, like some of the ones you were seeing previously. So the y-axis is the amplification if you're at a floor, what the component itself feels, and then it shows you that as the period of the component, that thing that's wiggling on that floor, as that changes, then the response changes. Okay, so it's you know, dispersed, but there's clearly a kind of a increase in the middle there around 0.5 second to 1 second, but it's more precise and more compelling when you normalize the T component with the T building. So this is a resonance effect. So when those two things are equal, you can see how there's this nice sharp increase. And then when those two things are not equal, either far to the left or far to the right, there's very little increase. So the dynamics of the component versus the building, particularly on period, you can see are pretty important and dramatic. And so capturing that effect properly is important to getting a good understanding of response. There's different places where ductility can come in, and I'll show you in a minute about the importance of ductility. So we take this, you know, rocking object, say it's a transformer or a, you know, cabinet or something like that, and it's got angles at the bottom. The component itself could yield and absorb energy. The angles at the bottom could be doing something, or the anchorage itself, if it were properly and luckily designed to be ductile. Sometimes that's impossible because of shallow embedments, but all three of these things are potential sources of ductility. Why do we care? We care because of this plot. So this is another one of these normalized x-axes. Okay, so we're talking about, you know, at resonance when the component and the building are in sync with one another at 1. The y-axis here is the component versus the floor. So there's a family of curves here, and elastic means, you know, no ductility. Nothing is yielded yet, nothing is absorbing any energy. So the elastic component has the biggest response, you know, almost a factor of 5 here. But if we put a little bit of ductility, you know, 1.25, 1.5, 2, you can see that there's this dramatic reduction in the response. So just as some things increase it, resonance, other things decrease it, ductility and the associated energy absorption. So to sort of cut to the chase, here's a kind of a key comparison of the equation as it is now and how it changed, kind of together with what I was explaining a minute ago. So ASCE 716, let's think of it as having 3 parts. So the 0.4 SDS, that is that's the ground acceleration, essentially. Okay, if you divide the peak of the short period acceleration by 2.5, then that's same thing as 0.4 SDS, and that is PGA. Then there's how does it change going up the building? So that's the 1 + 2 times Z over H. So if you're at the roof and Z equals H, that's a factor of 3, 1 + 2. And then there's, once you're at that elevation, whether it's the roof or the third floor, there's how does the component change with respect to what the floor is feeling. So that last orange one, that is essentially the peak component acceleration divided by the peak floor acceleration. So we have those 3 parts. We like those 3 parts. Those 3 parts make good sense technically. So in the ATC 120 effort, we said, okay, we're going to kind of keep the same 3 ideas. We're just going to make them a little more refined. So we didn't modify the 0.4 SDS. We just called it PGA. We did modify the 1 + 2 Z over H equation and what we're doing there is we're ratioing up PGA to get to PFA. We also acknowledge that building ductility, and the more building ductility you have, it's like a fuse or a filter, and it reduces the component response. So that was put on the denominator. And then the orange one, PCA over PFA, that's sort of the equivalent of the AP over RP effect. And then we also put some component ductility. That's the green RPO. Those were a little wordy or a little lettery, so to speak. So when it finally got into the NEHRP provisions in ASCE 7, we have these slightly more cryptic but shorter things that are the same. So the ATC 120 equation was essentially adopted with some wording changes, but in principle identically. So we're going to go into a little bit of detail on that and talk for a minute here about the height amplification effect. So this HF factor. So remember that was 1 + 2 Z over H. We tried to incorporate the period effect and this whipping action, and we also tried to acknowledge that it can be a lot less at the roof. So there are some situations where where it's really stiff, and so the maximum was set at 1 + 2.5 Z over H. So it's a little bit worse, but everything else, if you know your building period, TA, straight out of the building code, the fundamental code equation, we use that for simplicity. So you just need to know what your building system is and what your height is, then you know TA, then you can plug it into these equations, and depending on what that is, you'll get this family of the red, orange, yellow, green curves. And you can see there's potentially, depending on your system and height, a pretty serious reduction in the potential demand from this effect due to this more refined, but not too hard equation. Building ductility, which helps, and we wanted to acknowledge, and we wanted a simple way to capture it. This came out of the SEOC Blue Book a little bit, and is basically putting in the R factor and the omega naught factor and the importance factor. And then there's, for good measure, a square root sign in there. And this, so as long as you know what your building system is, you can get all this, and you can find out whether what your R mu value is. We decided everything should get more than 1. So we set the floor at 1.3. You can definitely get more than that depending on how ductile your system is. Then this effect of PCA over PFA, we captured through, it got renamed as CAR. So there's a lot going on in this table. So one thing we did is to say, well, if the component is sitting on the ground, maybe it's a emergency generator on a pad on the ground outside the building, in some equipment yard, or maybe it's up on the roof or an elevated floor. So that second category, the building, is going to come into play. In the first ground supported, there is no building. So that's not currently captured by the building code, but because we're getting a little more precise, we wanted to do that. So what happens is, the building can amplify things more than the ground can. And so we wanted to not overly penalize ground features. I had showed you the importance of component ductility. So we broke things into low, moderate, and high ductilities, which is very similar to how the RP factor has been done by code committees in the past. So that same idea comes into place. We just, the underpinnings of where we got the numbers, how did we get a CAR value of 1.8? Well, there is a presumption that that is on the ground. It has a component ductility of 1.5, which we're calling moderate, and there's a possibility that it is in resonance. When something is not in resonance, the building period and the component period are apart from one another, then you're not going to get any amplification. And I'll show you that in a little more detail in a minute. So the ones at the roof, you can see those, that final column, the numbers are a little bigger, and that's because the building is wiggling around, helping to amplify what the component feels. So what is this likely, unlikely to be in resonance? Remember, I showed you those pictures of the normalized response and how when the component and the building periods are in sync with one another, there's higher amplification. And when they're not, what we're calling the green unlikely regions, and it's a bit arbitrary where we cut the boundaries off, but this is the idea that we don't want to put a high amplification factor if something is unlikely to be in resonance. And this is essentially the way it has been done for decades with the RP and AP factors. Okay, so when you've got all those pieces of the puzzle, you will go to the same two tables that you're used to going to. One is for architectural components, one is for mechanical and electrical components. And the categories in those tables are almost all the same. There's been a few changes, and I'm going to highlight one here. So partitions, we decided that we would have some further refinement of those. You can imagine a taller, if you have a 18-foot tall partition, it's more flexible and it's more likely to resonate than if you have a stiff, CMU partition, or you have a short, sort of more normal 9-foot tall partition. So you plug in, okay, I have a, light frame over 9 feet tall partition, and what is my CAR? If I'm on the ground, it's 1.4. It turns out it's 1.4 also in this case. If it's above, the ductility that we think is included in partitions from yielding metal and the chipboard absorbing energy gives us a 1.5 factor. And then there is an omega factor associated with that component that now has a subscript P. And we're trying to be careful not to confuse this omega with the omega that we used to design the building structure with. So we deliberately added this P in there because they're definitely not the same thing. Okay, so that was a whirlwind tour through the design equation. Now I want to kind of talk about a little bit more stuff that has gone on. And so one of the things I was highlighting before is that the way we think of components that are sitting on platforms or distribution systems will change. And so traditionally, the design, say, of the middle element here, some mechanical equipment on a platform, the design of the platform was totally dependent on what the AP and RP values were for the thing on top of it, which doesn't make any sense technically. If you have a moment frame platform or you have a brace frame platform, that's what matters. And the thing on the top is just weight that's adding to it. So now you're designing the platforms based on the platform characteristics, not based on the thing sitting on top of it. Distribution systems, same idea. If you have, not that you would very often, but if you had a moment frame kind of system, or if you had a a tension rod system, or if you had a rigid brace frame system, we have values for that. It doesn't depend on what kind of pipe is going through that, because that's not what matters. What matters is the ductility and the system of the bracing. There is a not very often used but important feature that's been in the building code for a long time of how do you use nonlinear response history analysis to design or to provide values you can use for non-structural elements. We have adapted that idea. We have used the new equation, and what we changed is this thing in the middle, what's called AI. So this would come out of your response history analysis. It would be the acceleration at the floor, and it would just replace the default HF RMU values. So pretty straightforward way to apply it. We have adapted the omega naught P value, made sure it's distinct and clearly different from omega naught for the building, but we have harmonized it with the values of CAR and RPO. And then we've updated those things. So now the tables, as I showed you, have these as in the headings compared to the AP and RP that they used to have. There have been some other adjustments, minor ones, in primarily clarifying some things. What's the design criteria? We have explicit load combinations now. Some discussion about how big can the weight be before you have to do certain things. Penthouses were a bit of a loophole in previous codes. You could literally, in theory, design an unreinforced masonry penthouse in seismic country, which didn't make any sense. So now it's much more clearly tied to building code requirements, but there's a lot of flexibility. So there's multiple ways to do a penthouse, but you got to kind of follow the associated rules with those. We did not change the minimum and maximum equations. So even though I've talked a lot about the basic equation 1331, the top, the high bound didn't change and the bottom didn't change. And then that's based on research. So we vetted those and were sort of pleasantly surprised to find that they represented good bounds and we were going to keep them. We haven't changed the way displacements are adapted or addressed, or the way component periods are calculated. There were some modest changes to chapter 15, the non-building structures chapter. There's lots of, when you get in the big time industrial world, there are some big things that go between structures of all kinds of different shapes and sizes and characteristics. So designing elements that couple systems was clarified, and the weights that go into threshold values of when you have to use chapter 15 was revised based on some research, and a whole new section for corrugated steel tanks was added. Otherwise, pretty much similar to what it was before. Okay, so I'm going to take a breath and we're going to move into some design examples now that you're all experts on the component design equation. So we have one that I'm going to focus on, the precast panel on in some detail, and then I'm going to highlight at the end of these other systems. So these are drawn from this design example guide. They all have kind of a look in them. So, what is the component? This one we're going to put in a steel moment frame building. It's an office, it's a risk category 2, and thus it has no special component importance factor. It's not part of the life safety system, for example. 5-story building, high seismic country with an SDS value that's pretty big. So 4.5-inch thick stuff, there's glass in there, steel building behind that I'll show you in a minute that holds the thing up. So here's an elevation on the left, sort of big picture elevation. You can see the 5-story steel frame building with beams and columns. And then there's kind of this repetitive pattern of glass in the middle, long glass, some short column covers at the end, and some wide spandrels above and below the window. And then there's a blow up on the right where you can kind of see those pieces and you can see the dashed lines of the steel framing behind. So one of the things that I think is important and is neglected in the collaboration between architects and engineers until sometimes it's a little too late is you want to be talking with the architect early on about how are we going to accommodate interstory drift. And why does that matter? Because there's going to be joints somewhere and they're going to be, you know, tough to deal with, particularly when different systems meet one another around corners. And there's different ways to do this. So you can slide. So you can, the picture on the right, we're sitting that panel on the floor below in a bearing connection, and it doesn't change. It doesn't rock or tip. It just stands vertically. So something has to have a horizontal slot or a slip plane at the top to let the upper story move with respect to the bottom, as opposed to rocking, where the panel is kind of pulled by the move. In that case, the floor above moving to the right, dragging it along, tipping it up on that bottom right corner. So you got to know what kind of systems you have and how they interrelate in order to design this precast element and to properly give it the space it needs. So let's look at that in a little more detail. And you can see how tricky this gets. So we've got those deep, long spandrels above and below, and these narrow, short covers on the columns. And then we've got 6 pieces of, you know, windows in the middle. We're not showing in this picture the window heads and the mullions yet. Okay, now I'm going to push the building to the upper floor to the left, and the spandrels are anchored to the floor above and the floor below, and so they don't move sideways, or they don't rock, they don't tip, they just get dragged along for the ride, as opposed to the column cover, which tilts, and the glazing, which tilts. So one interesting thing about this, it's not sort of sometimes widely appreciated, is that since the spandrels are staying as rigid objects, that means the full interstory drift has to be accounted for in the shorter height of the column cover and the glazing. So that can make it more challenging if you have not appreciated that. So now let's blow this up in some more detail and look at kind of a schematic view of how window systems work. So on the left here, we've got, you know, some blue panels. We've got some purple mullions. And if you look down in the middle here at the bottom, where that's a section looking down, you can see the rectangular mullion, which might be a tube, and then it has this black thing that sticks out from it, and it captures the glass inside there. And then there's similarly on the sill, and the head would be similar. The windows are sitting on some shims or some spacer blocks, usually not right at the corners of the glass, and then they're in this kind of U-shaped channel. Now we're going to, on the right, we're going to deflect it. We're going to tilt that thing to the left. Well, the glass doesn't change magically from a rectangle to a parallelogram. It just can only stay as a rectangle, otherwise it would shatter. So the glass is going to tip up on one of these spacer shim blocks. So it's going to tip up on the one on the left when we push it to the left. And that means the upper right corner is going to go up. And if it goes up too high, it hits the top of the head. So you have to have enough vertical space at the top to accommodate that lifting. And then you have to have enough horizontal room in the vertical pieces of the mullions to allow it to move in there. Okay, so, you know, window suppliers and designers, this is what they worry about every day. Okay, so now let's get to some numbers. So remember I was talking about that table. So same table that you're used to going to, you go to the architectural components table. And for those of you who've done this before, you know there are sort of 2 categories for cladding. One is for the body of the cladding, the wall element itself, and those have lower values. And then the fasteners have higher values because we don't want them to be the weak link. So we conservatively assign high values to fasteners, and in that case, the CAR value is higher. We decided the component ductility would be similar to those. We would change the CAR value, and then we would associate the overstrength factor and correlate it with the CAR. It doesn't make sense to design it for a high value and then yet to have yet another high value on ductility when you're essentially making it elastic. So those were coordinated with one another better than they have been in the past, I would say. So what do you need to know to figure out the design force? Well, remember I told you the steel moment frame, which has an R of 8 and it has an omega naught of 3. I gave you the SDS before. We said it was an office building with an IE of 1. We don't have any special life safety issues with the cladding. Redundancy for cladding is 1. We're going to put this at level 3 in this, 40 feet up in a 67-foot tall building. And here's some numbers about how much do panels weigh. Normal weight concrete in this case, and that panel is about 9,000 pounds. The glass above it, 1,500 pounds. Column cover is smaller, so it weighs less. The period of this building, the steel moment frame building that has, 67 feet tall, and we have the CT value, so a 0.8 second period. Okay, so getting up there. Kind of at the peak or on the downward side of a typical response spectrum. So we're going to take that 0.81 factor and we're going to put it in that equation for HFs. So, A1 comes from that first line, A2 comes from the second line. You get those values, you plug them into this, obviously, statistically derived thing, which has a weird exponent of 10 on one of these things. And you end up with 1.74. Okay, so that's our amplification factor. And that is noticeably less than the maximum value that you could have had if we didn't account for that. So the ductility factor for the building is R mu, and we have that 8 value for R and we have the 3 value for omega. So we get a steel moment frame, has a decent amount of ductility. So 1.7 is our factor there, above the floor of 1.3. There have always been some reminders in the code. We didn't change those. I'm bringing up here a little awkwardly, but as a reminder, we don't want the component to cause the failure of anything essential. Okay, so that's not much of our problem here. You have to be positively attached, right? So friction doesn't work. You got to be welded, you got to be bolted, you got to be something that we call quote unquote positive. We're going to put loads at the center of gravity and we're going to distribute them as appropriate depending on how complicated they are. We're going to account for relative displacements, which I'll show you at the end. And then we got to make sure that those relative displacements are incorporated, as well as the ability to expand and contract, because this is outside for temperature. Okay, so let's say that we look at this spandrel, in this case from the outside in, and it is spanning across. There's lots of different ways to do this. This may or may not be a typical one. This guy has 6 supports, 2 at the ends and 2 in the middle. So at the ends, there's an A1 at the top, which is what's called a push-pull connection. It doesn't take vertical loads. The upside down triangle, that's this common symbol for bearing connection. So this spandrel spans in bearing between A on the left and A on the right. That's its deep direction. And then it spans out of plane. All of these connections are holding it back out of plane. So in its thin direction, it was braced in the middle at those BB points. And what you're seeing on the right is a section at the middle. So there are reactions at the push-pull connections that are pushing in and out because of the eccentricity. So the loads pull down and they rotate that thing, and those loads go into the slab, or they go up through this kicker back to the slab. So let's calculate some forces. So remember, I was telling you that the panel and the glass, weighs about 8,700, 1,500. So there's 10,000 pounds of weight that spandrel is supporting. And we're gonna plug in the SDS values, all these other 4 variables, and we're gonna end up with 0.40 WP. Okay, so FP over WP, 0.4 G is the new design equations acceleration. The max and min are unchanged. And you can see in this one that the minimum, that 0.3 SDS governs. This is a common occurrence. It was a common occurrence before, it'll still be a common occurrence. So the higher up in the building, that would have not been true, but it is at this particular level. So you end up with about 4,500 pounds of design force to deal with. So you gotta, use those earthquake, FP, QE forces. Rho is 1, so EH doesn't, change. There's an EV, a vertical component. The 0.2 SDS is unchanged. So it's, it's a decent value, 3,000 pounds going up and down together with your horizontal value of 4,500. And then you use, and now it's explicitly says to use these basic load combinations that you use for everything else. So, you plug in the different numbers to those. So, as a designer, if you're looking at this in elevation, it would be spanning as a simply supported beam in its strong direction, WL square root 8 kind of thing. In its weak direction, it's, 3 supports. So you get moments that look like that. And you can calculate those values. We go through the 1.4D and then the earthquake one, and earthquake, not surprisingly, governs in this case. And there's a vertical moment in the strong direction and an into the page moment in the weak direction. There's also the 0.9, there's the 1.2D and there's the 0.9 where you're subtracting things, and that is not going to govern in this case because all those values were additive before. All right, so that's the panel itself. So that uses the kind of the lower category with the lower CAR, or similar to the lower, what used to be the AP values. Let's say we were designing individual connections in there of like the panel to the building, or if there were screws in this, so there aren't, but in cladding that had that. Then we have many of the things are the same. HF, RMU, SDS, IP are all the same, but the CAR value is different. It has that higher one because we're trying to be more conservative. So now instead of 0.4, we're up to 1.1. That means that becomes the governing one in this case. So it isn't that the minimum governed like it did before. And you can see this is a big effect. This is basically tripling the design value when you're looking at the thing that we want to worry about and not have be the weak link. Knowing where this is a bit of an art. So this push-pull connection would typically be an example of that. The design example goes into a lot more detail about how you resolve all those things and what the numbers are. But free body diagrams are important, and resolving the forces just like you're used to doing with statics is still part of the deal. Okay, so let's talk about drift for a minute. This is a snip from that picture I showed you at the beginning when we were talking about how do things slide a rock. So this is a rocking glazing and a rocking column cover system. So if we had a 13.5-foot story height from top of steel to top of steel, and we were trying to make it work for what the code allowable limit is, in this case 0.2 times the story height, then this would transform into a little over 3 inches of movement, which is a pretty big number that would have to be accounted for. And because we don't get any benefit from deformation or rotating or anything with the spandrels, we got to account for all that 3 inches, down in the middle there. Now that the requirements for glazing and accommodating drift, which have been in the chapter 13 in the building code for a long time, they're unchanged. So they come from research and AAMA testing strategies that have been around a long time. So there's a number of them. They can be satisfied in different ways by testing, by analysis, by using specific things that are considered, less worrisome, but you have to meet certain criteria about, how tall it is and whether it's fully tempered or whether it's in a specific pocket. You can see this last one, it gets awfully specific. That's coming from some research long ago. So let's sort of examine that in a little bit of detail because I thought it's sort of interesting as I was digging into this equation. Where does this come from and what does it mean and why are the numbers that way? So think of this picture on the bottom where the glass is a rectangle and it's sitting on some blocks, and the mullion system, this racking frame of tilting elements that turns into a parallelogram when we push to the left, moves, and eventually the upper right corner of the frame hits the top of the glass and starts to, touch it. Okay, now if we move the racking frame, we're dragging it farther to the left because the upper floor is pulling it along for the right. Now it starts to push the glass because it's in contact at that upper right corner. It pushes it to the left until it hits the bottom left corner. Okay, so that's the maximum translation that you can get. And so part of this equation is from translation. And another part is once you've translated as far as you can go, then it can start to lift up. And due to the kinematics, if you go through the sort of geometry, you'll end up, in fact, with that equation and it hits the corners. So now you've run out of room, everybody's in contact, and if you kept pushing it, you would get a diagonal strut running from the upper right to the bottom left, and then you'd start buckling and eventually breaking the glass. This presumes that things actually bear at the corners, and that's not necessarily the case when some shim blocks are there, but this has been the traditional basis of this assumption. Okay, so now I'm going to give you kind of a quickie tour of a few more slides, and then we'll wrap up of the other examples that are in this NEHRP design examples guide. So one is about piping. So we're looking down in plan here of a piping system which has multiple runs of piping. It's supported by trapezes that have longitudinal and transverse braces. Some of those pipes go up and down. Some of them turn sideways. Some of them have to cross joints. So, this example in the design guide talks about all of that stuff. There's another example about stairs where we kind of go through how do you calculate the forces for stairs, which parts of the stairs are the fasteners that have higher demands. That came out of the Christchurch earthquake where there was a lot of stair failures, and the code writers decided to be more rigorous about certain elements. We talk about drift in that example and how drift induces forces as you drag the thing sideways, and you have to combine those with the inertial forces, the FP forces. There's an elevated vessel example. So this is an interesting one because of this issue about the support structure. So here we've got the thing, this vessel on this table, and the table has, tension rod X bracing here. So you got to design the thing to be anchored to the table, and that uses its own dynamic characteristics. And then it's a little bit like a two-stage analysis in a building. Then those loads get imparted on the table, and you have to design the table for its R value. And there's sort of a R of there's several categories for those equipment structure tables values, and they come from the mechanical grand table, just like the component values do. So that design guide, highlights things in green, and this is a reminder of what I was just saying, is that we've got those forces in the top that come down on the tabletop here, and they have their design values, and then they get combined with the design values associated with the brace frame structure. And here's how one would derive those. It's that same equation I've been showing you. You plug in, depending on where your height is, depending on what your building system is, the HF and R mu values, the CAR value and the RPO value, similar to AP and RP. They come from the mechanical chapter. So I was showing you the table for architecture and partitions a few minutes ago. Now I'm showing you where do you get the values for that platform? If it's a decent lateral system, then you have a little bit better because there's more ductility of these, in this case, CAR of 1.4 and RPO 1.5. If you were less ductile, you'd have 1.8. If you don't have systems that qualify, and there's descriptions of this, then you have the highest values. And then there's a fan unit design, both if it's on vibration isolators or if they're just cast into the concrete housekeeping pad, because that has not really changed. So the idea of, vibration springs amplify things, and you better worry about that, is captured still. So I keep mentioning these NEHRP design examples. Here finally is a picture of the first volume 1. Okay, this is a kind of a 3-part series of documents that FEMA funded through the Building Seismic Safety Council to produce this, and there were a number of authors. I was the coordinator of this, and volume 1 is a very thick book of design examples and equations and overviews of how things got there, and it talks about new systems that have come in the building code with this latest edition, and talks about diaphragms, talks about non-structural elements in chapter 8. Volume 2 is a whole slide series for all these different chapters and the different topics, and then there's a sort of helpful flow chart volume that helps you to understand all the things you have to do and in what order to do them. Little known, but valuable, particularly if you're new to the game. And these are the links. So these are all free. It's from your friendly federal government, and so you can just click onto these things. And I checked it yesterday. It still works. All right, so we are gonna turn it over to questions and answers.
Great. All right. Thank you, Brett and Marianne. So we've got a little over 15 minutes for question and answer, and we got a whole lot of great questions. So we're going to start picking some of these off. The first one, in general, have the changes to the FP equation resulted in more conservative design forces compared to ASCE 716?
Why don't I take that one? So I'm impressed. That's probably the most key question that any practicing engineer, any owner, any contractor, any vendor who sells this stuff would want to know. So the short answer is it depends. So sometimes they go up, sometimes they go down, sometimes they stay the same. The majority, like kind of on average, it goes down. We did this rather incredible set of spreadsheets that one of our colleagues who was intimately involved in ATC 120, a man named John Gilligarden, who's sort of a non-structural guru in the industry. He and I put together these Excel spreadsheets that basically compared all the different combinations for all the different things, and then we highlighted, you know, the ones that went up and the ones that went down and ones that stayed the same. So that's been rather extensively vetted, and on average things go down, but it definitely depends. If you have brittle things in a non-ductile building, they go up. You know, if it's the other way around, they might go down.
When using the new FP equation, are there recommendations for choosing the most appropriate R and omega naught values for historic buildings that were designed before the current values in table 12.2-1 came into being?
Great question. Yeah, we agonized over that. So, and it's not an easy thing to answer. So yeah, we did put in some kind of some default values, and then there's discussion in the commentary about how to apply that to different situations, because we recognize that, you know, we're obviously going to put and we hope design anchorage for components in existing buildings, not just new buildings. So yeah, we have that covered.
Do you want to talk a little bit about that at all?
No, I think there's so many questions. Why don't we skip on?
Okay. Brett discussed amplification of input to a component due to the component period relative to the building period. The example shown was for a tall multi-story building. The amplification seems appropriate for tall buildings. However, was this impact investigated for 1- and 2-story buildings?
Yeah. So yes, what we did is there were a professor, Professor Medina, was on our key research team, and one of his graduate students did a whole series of nonlinear response history analyses using archetype buildings or prototype buildings that were intended to represent different heights, different structural systems, different periods, and even different ductility. So we had ones that were sort of designed right to the wire, and ones that were designed more realistically that would have overstrength and thus would take longer to get to yield. So we did look at all these different scenario or different cases, different archetypes, and tried to draw conclusions. It's not exhaustive. I mean, they did an amazing amount of work, which is rather mind-boggling. But there's so many possibilities and permutations out there. We had to kind of pick our spots. But height and building period and stiffness, moment frame versus shear wall, yes, we definitely looked at that.
Why did we choose PGA as an intensity measure for the ground motions? Could PGA capture all the essential attributes of the expected ground motions, which translate to non-structural damage? Are there enough data or studies supporting that PGA correlates well with the damage measures of non-structural components?
Yeah, that's a great question. Well, the sort of honest answer is that was easy, and that was what was in the building code already. Remember, I showed you those, what's in ASCE 716 versus what's changed. So that 0.4 SDS has been around for a long time. Remember, we're partly capturing building effects, you know, in the other variables, but we are not explicitly capturing almost any of the things that you talked about in the good question. And it's just way beyond the kind of practical scope of what one could do for this. And I don't think the research is really out there to justify that. You know, that was really not even on the radar screen too much. Yeah, Marianne, you want to?
Yeah, I'd like to add a perspective to this one, because what we're really lacking is the ability to translate actual earthquake damage to non-structural components in a meaningful way to create refined procedures. So we don't have the data from earthquake records that show us this thing on this type of building, you know, had these kinds of demands on it. We just don't have enough post-earthquake data and information to build from. And so one of the recommendations from the ATC 120 project, which we didn't talk about, is that we need to collect quantitative information that would someday allow us to actually, consider other things that, might be also important, but that we simply don't have the tools, the information from which to study it.
Yeah, we do have a shake table testing, some of which is proprietary. And we do have these analytical studies, but Marianne's right, the hard, real truth of, we have an instrumented transformer on the roof of a building, and we know its dynamic properties, and we know everything about the earthquake. I mean, that would be the nirvana, which we just really are lacking, and we hope to get as the years unfold.
Can you address if there are options for non-structural anchorage of components if the lateral system of the building is unclear? We often get involved in seismic anchorage of components without getting much information about older buildings and renovation projects. And then a related question, what if we have the component information but don't know the building period? Are there assumed values that allow for seismic force calculation?
Yeah, there are default values, and precisely for this problem. However, you're not going to like them because they're bigger, right? I mean, and why is that? Well, you could have a crummy, brittle building that doesn't have any ductility, and so why should you be able to use the best values? So what's the message there? The message is don't accept that. Okay, like how hard is it really to figure out what the lateral system of the building is? We got this, comment repeatedly during the code development process from a variety of parties, saying, this is kind of the deal. I mean, somebody calls us up and they says, give us a price to design these components, and they tell us nothing. Well, okay, but they could get better pricing, they could get cheaper designs if they went the extra inch to tell you what the lateral system is. So the code is now encouraging that. You don't have to, but the forces are going to be higher because we know they matter.
Marianne, anything you want to add to that?
No, he's got it.
Was historical impact from vertical accelerations looked at? Does the 0.2 SDS adequately consider vertical accelerations on non-structural components?
No, we did not study vertical impact. Just only so many things we could do. So that was left as is.
Has there been any analysis of construction cost implications for implementing these revisions in new critical facilities?
Nope.
Can we talk a little bit more about that?
Sure.
Please.
Brett said that on, some of the design forces went up, some of the design forces went down. And the upcoming code did not fundamentally alter the numbers of things that we anchor, restrain, or brace. So in terms of the code compliance, the cost to do it to the current ASCE 7 versus the future one should not be very different. I mean, depending on what the thing is, it might go up a little bit or a little bit down, like the forces, but I would expect that there should not be a very measurable change if everybody's playing fair. So that's my thought about that. The other thing is that, and another interesting question is, well, what about when you want to achieve, even enhanced resilience? What's the cost of that? Which is something that many owners are thinking about right now, in recognition that, the code doesn't necessarily worry about function and after an earthquake. So if we want to achieve post operations in our, first earthquake operations in our building, we need to do more things. We need to worry about more things. Maybe we need to anchor and brace more things. And there is a cost associated with that. And so there are many owners who are currently in the process of projects and trying to weigh the costs and benefits of that kind of enhanced performance. And there's some work out there, some projects where there's information that talks about a few % of increase for achieving some enhanced performance, but it varies building by building, building type, building function, and what you're really trying to achieve.
Are there any provisions for unanchored components? In nuclear power plants, it's permitted to use the methodology of ASCE 416, Chapter 11 for unanchored rigid equipment. In the subject approach, the equipment is analyzed as a rigid body under the vertical and horizontal accelerations of the structure of the equipment location, and conservative estimates of the sliding displacement and overturning potential are made.
No, we did not adapt that idea to your average everyday design. You know, there are sliding things for PV panels on the roof that got in the code a while ago, but other than that, no. That I'm not sure how practical that is in your average building. You know, that there's a huge amount of analysis that those folks are doing to justify that. That's beyond, far beyond what would be acceptable to any owner, I would imagine.
You'd have to come in via the alternate means of compliance and
Yeah.
make the case for your thing. I've done something once, you know, in my 40 years where it was a thing that was, you know, many millions of dollars, and the thing couldn't be anchored down at the bottom, and it was robust. And so that was the one time I've ever had to go down that path. So that's how you have to go down it, though.
Okay, I think this will be our last question, and then Brett, I'll need you to
Yeah.
bring back up the slides. But
I'll do that right now.
so in developing the new equations, was building overstrength considered for the building R factor, meaning that a building may not have as much yielding as assumed, resulting in a higher component force. This could also occur at a shaking level below the design shaking, which has minimal building yielding.
That's another great question. Yeah, very thoughtful, and you're absolutely right. And we tried. So remember, I was talking about the archetypes and how we were trying to sort of capture different characteristics of flexibility, of height, different lateral systems. We also tried to capture different levels of sort of actual ductility. So we had some archetypes where they were designed kind of right at the wire. Everything was, you know, right at, you know, 0.95 or 1 at the limit. And so there wasn't much free overstrength. And then we had other ones that were noticeably more than that. So you can imagine like your average moment frame, which is typically drift governed, has inherent overstrength because that's not the governing factor. So you just keep pushing and pushing it, you hit the drift limit, and then you keep pushing it some more and you have more force capacity. So we did try and account for that. But there's only so many versions we could do, and there's only so far you want to go. It's like, how much overstrength do you really want to account for? It definitely matters, and there's no way to practically make that a provision in there. So we just tried to say, okay, we studied that, and our equation works pretty well at both bounds, the one with a lot of overstrength and the one with not a lot of overstrength. But a really good question.
Mary Ann, anything you wanted to add?
No, that was a good
No.
answer.
Great. Okay. Thank you both. Okay. Brett, if you could move forward a slide. So I just wanted to take this opportunity to let everybody know about the 5th International Workshop on Seismic Performance of Non-Structural Elements. Hopefully if you're attending this workshop, this means this topic is, this webinar, it means this topic's of interest to you. It's going to be taking place at Stanford University in Palo Alto, California on December 5th to 7th later this year. The workshop's being organized jointly by the Applied Technology Council, the European Center for Training and Research in Earthquake Engineering, and the International Association for the Seismic Performance of Non-Structural Elements. The workshop's going to be hosted by the John A. Bloom Earthquake Engineering Center at Stanford University. Brett Lazundia, one of our presenters today, will be one of the keynote speakers, as well as Carrie Ryan at the University of Nevada, Reno, and Jan Stanway at WPS. For more information about the technical sessions and topics, and for registration and sponsorship opportunities, please visit the website displayed on the screen. And then Brett, if you could move forward our last slide. So on behalf of the Applied Technology Council, I want to thank Marianne and Brett for their presentations and for sharing their experience, knowledge, and insights during the Q&A. I wish we had had more time for the Q&A. And thank you to everyone for joining us today. As a reminder, for those who registered today, expect to receive a follow-up email with a link to the recording of the webinar and a link to a participant feedback survey. And please provide your feedback because we use that information to continuously improve our program. For those who registered today, you'll also receive a separate follow-up email with a link to purchase a PDH certificate. I'd also like to briefly mention that ATC provides trainings for organizations on a variety of topics like building safety evaluations after earthquakes, windstorms, and floods, as documented in the ATC 20 and ATC 45 manuals. So for more information on that, please visit our website.